All right, everybody, welcome back. This is going to be our first asynchronous lecture. Um, so I'm going to try to get through some of the material from where we left off, which was basically right at the beginning of talking about the equipartition theorem, or the equipartition of energy. We're not necessarily going to prove the theorem here. And I'm going to hopefully get up through compression work, but we'll see how much time I have. So yeah, view this at your leisure and make sure that you've watched all of it by the next lecture, which will be Friday, February 5th. Okay, so let me switch over to the Blackboard and we'll get started. Okay, so here's where we were earlier today. We had just, what had we done? We had just found out the relationship between the average translational kinetic energy and the temperature T. And so we considered basically, go back. We had considered this cylinder and we had talked about a particle bouncing down and back and the kind of pressure that that particle bouncing off of the cylinder, off of the piston exerts. And in the end, we found this expression which relates the average translational kinetic energy to 3/2 K, the Boltzmann constant, times the temperature T in Kelvin. And I'd also just talked about the different units of measurement, namely the more useful unit of measurement for roughly room temperature stuff, which is electron volts. And for electron volts, you have basically KT at room temperature being roughly 1/40th of an EV. Okay, so let's move on. So now we are going to talk about the equipartition of energy, which is 1.3. So the result that we just showed is basically a specific case of the more general result called the equipartition theorem. So this result that we just showed before, and we did have a bar before, but I'm just going to leave it off for now because we're going to assume that all of our systems are so large that the difference between the averaging and the non-averaging doesn't actually show up at all. So this is what we showed. We show that it's 1/2 KT for every single direction, X, Y, and Z, which gives us 3/2 KT. So this result is a specific case equipartition theorem. And so what the equipartition theorem says, well, it says that for every type of energy that comes from a quadratic position of velocity, that it gets its own 1/2 KT. So for every quadratic, meaning like it's like x squared, like a spring block system, or it's got something like v squared, just a typical kinetic energy. If it's got something quadratic like that, then it can basically be treated as a simple harmonic oscillator, and you get this result. So for every quadratic contribution to the energy, you add factor of 1/2 KT to the total kinetic energy. Okay. So some common expressions that are quadratic like this we know and have seen many times before. So we know we've already just been dealing with this 1/2 mv squared, where v could be x, y, or z. So I'll just leave it as v for now. You're probably familiar with rotational kinetic energy, 1/2 I omega squared, where I is the moment of inertia, omega is the angular frequency. You could have an x, y, and z there as well. And then a spring energy, kx squared, where you could also have ky squared, kz squared as well. So given a system of n molecules, molecules and particles, it doesn't really make a difference, n things basically. We'll take them to each have f degrees of freedom. And I'll use DOF to refer to degrees of freedom for shorthand. Okay, in that case, the average thermal energy of the whole system is going to be given by this expression. So it's going to be the number of things, particles, molecules, whatever, the things that have the degrees of freedom, multiplied by the number of degrees of freedom that each of them has, times the 1/2 kT contribution that we just showed a specific case of before. So like for before, the result that we were showing was basically n equals 1 and f equals 3. So we had one particle that had 3 degrees of freedom, namely 3 kinds of kinetic energy in the x, y, and z direction. Okay. Whatever. Okay, so keep in mind that this does not include kinds of potential energy like chemical bonds and rest energy. So energy in bonds and rest energy, etc. Okay. So how do we know how many degrees of freedom there are for a given particle? Well, that's honestly something that you're going to have to determine either by just looking it up for now, or in the real world, you would just be like doing some kind of experiment to determine it. So for now, you're just going to have to accept that I'm going to give you what the degrees of freedom are. So example 1, we can draw a little picture. We're going to say that these all have 3 degrees of freedom. So basically they can move in the x, y, and z direction, and that's it. So we'll refer to these as monatomic molecules, which just means it's shorthand for saying that they have 3 degrees of freedom. Okay? So let's try to draw something a little bit more interesting. So those were just point particles. They don't have any rotational kinetic energy or anything like that. But if you wanted to add that in, now you could make them like extended molecules like so. So you've got like, I don't know, like a hydrogen molecule or something, although that would have like a hydrogen and 2 oxygens. So this is just some bar. Who cares? And these things are flying around. They have some kinetic energy, but they can also have some like rotational kinetic energy, right? So these guys can be rotating. We're going to silence that. Give me just a second. So these are called diatomic. So they have translational degrees of freedom plus 2 rotational degrees of freedom. And so you might ask, well, why just 2, right? You can rotate it in 3 different ways, right? Well, the thing is that rotation, so let's expand this out a little bit. So here's our diatomic molecule. So rotation about an axis of symmetry, like this. So rotation about this axis, right here, rotation like that, does not count as a degree of freedom. Rotation about this axis and rotation about like the axis coming into and out of the page do count. So it only has the 1, 2, right? So in all, it's going to have F equals 5 degrees of freedom. Okay. Now, if we wanted to bump this up just a little bit further, we could try to draw molecules that don't have an axis of symmetry, and I'll try my best here, but this is all I got. Something like this, where think of this centerpiece as being extended a little bit out of the page. I'll try to do that again. So basically these are molecules that have no rotational axis of symmetry. So in this case, well, we get less creative and we just call it polyatomic. So it's got translational and it has 3 rotational. So adding this extra non-symmetric rotation just obviously increases the degrees of freedom by 1 relative to this guy, the diatomic molecule. So the degrees of freedom here are just 6. Okay, so another question we could ask ourselves. How many degrees of freedom for diatomic molecule that has a vibrational degree of freedom? So the picture for this that you should have is something that has some extent, and we're going to model the interaction between the 2 pieces as being a spring, so it can stretch back and forth and whatnot. So from vibration, you're going to have both, well, the 1/2 kx squared, so it'll be 1 degree of freedom, but you'll also have the kinetic energy just due to these 2 pieces right here moving at some speed, not k, mv squared. That's 1 degree of freedom as well. So vibrational degrees of freedom contribute 2 total. And then, as usual, the translations, they'll contribute 3 degrees of freedom. And then the rotations, we already determined that this is going to be like a diatomic molecule. So it will contribute 2 rotational degrees of freedom, because the symmetric rotation doesn't count. So we have a grand total of 7 degrees of freedom for a diatomic molecule. It's modeled like this. But one thing to note, just in practice, at room temperature, most gases actually have their vibrational degrees of freedom so-called frozen out, because you're not at an energy such that the vibrational degrees of freedom are actually activated. So let's note that at room temp, of gases, they're frozen out, so they just don't contribute. So for example, your typical air molecule will, in practice, at room temperature, have 5 degrees of freedom rather than 7. So just a tidbit of information. Solids, they typically have 3 vibrational directions, but they're fixed in place, so they don't rotate or anything. So typically they'll have 2 times 3 equals 6 degrees of freedom, because you have 3 vibrational directions, and then we have 2 degrees of freedom for each of those, like we had just said before. So 6 degrees of freedom for a solid in practice. But again, at specific temperatures, and namely at room temperature, some degrees of freedom can also be frozen out, just like in the case of gases. So this is always going to, degrees of freedom is always going to have to be something that you're given for the most part. And last but not least, liquids, typically more complicated. Because the interactions between the molecules in a liquid don't typically follow a nice quadratic like energy function like in the solids and the gases. So we'll just leave that. All right. So that is basically our discussion for the moment of the equipartition theorem and kind of how it pans out in practice. So now we'll discuss 1.4, which is heat and work. Okay, so we've got a number of concepts going on at this point. We've got temperature. We've got energy. We've got heat. And now we're going to talk about work. So a common mistake that a lot of students make in thermodynamics is mixing up all these different concepts because they do typically relate to each other, but they aren't the same, right? So let's just label them. So we've got 1, 2 for energy, 3 for heat, 4, and let's just point out the differences real quick. So as we've discussed before in our definition of temperature, it's basically a measure of the tendency to spontaneously give up energy. Spontaneously. Okay. 2 is energy. Energy is just going to be to us, it's just going to be a fundamental, which the word fundamental is kind of confusing because like, what the heck does that mean? But we won't get into how you actually define energy here. We're just going to think of it as a fundamentally conserved quantity. It never gets created, never gets destroyed. It just moves around. Okay. 3 is heat. So heat, we've defined before as well. It is the spontaneous flow of energy. Note the word flow here. It is not energy itself, but it's the spontaneous flow of energy that we call heat. And it is caused by a change in temperature or a temperature gradient or something. So you only have heat flowing when you have a cold object in contact with a hot object or something like that. Then heat flows from hot to cold. And 4 is work. That's going to be any transfer of energy into or out of system that is not heat. So think of this more as like a bulk motion. So where heat is like the spontaneous like random motion of the particles moving around and the energy associated with that, work is going to be more of a bulk motion being applied to a system. Okay. So at this point, let's lay out the implicit assumption that we've been using all along, and I think I might have described this earlier, but it often gets the name the zeroth law of thermodynamics. What is it? Well, it is basically just the assumption that two bodies in contact come to thermal equilibrium. Not necessarily assumption, it's the observation that this actually happens. So two bodies in contact come to equilibrium. All right. Now we're going to introduce the first law of thermodynamics. The zeroth law is called the zeroth because it's kind of an underlying assumption. I mean, it's not really something you generally think of too much. It just exists in the background. Okay, so what's the first law? Well, it is that the change in energy of a system is going to be equal to these two letters added together. But what are the letters? Well, Q is going to be referring to the heat entering the system. What's W? Well, you can probably guess. It's related to the work, but specifically, it's the work that is done on the system. So this is heat entering, and this is work done on the system. So you might see other versions of this where it's, rather than being Q plus W, you've got Q minus W. So in those cases, W is actually defined opposite to what we have right here. If you see a minus sign in front of W naturally in the first law of thermodynamics, it's actually telling you that W is the work that the system does out on something else, okay? So here, the convention we're taking is that we're going to put a plus here, and then we'll refer to W this way. All right. Next page. So what are the units corresponding to heat and work here? Well, we know that they're both forms of energy, and you know that the unit of energy, the SI unit of energy, is the joule. Which is just defined as 1 kilogram times meters squared per second squared. So what unit should we use for heat and for work? Well, oddly enough, people started talking about heat before they really realized the intimate relationship between heat and energy. So they used a different unit. They used the calorie. Which is kind of weird, but whatever, we just got to roll with it. So 1 calorie is, in today's modern language, it is equivalent to 4.186 joules. So just know that, I mean, obviously heat and work, they all have the same units as energy. It's just that historically we've used calories for heat, and 1 calorie is just related to joules via this relationship right here. So not confusing. You're probably familiar. Ooh, I should have been careful here. So when I wrote calorie right here, I should have made this a lowercase calorie, because actually the uppercase calorie, so if you see the C being uppercase, that's actually a kilocalorie, which is defined as 1,000 calories. And so this is more relevant in general to food, right? You'll see that if you look at the box of your morning breakfast cereal or something, you'll see how many calories it contains. Okay, and since we're on the topic of heat, we're going to talk about the different categories of heat transfer, the different methods that heat can transfer between objects. Well, what are they? So one that you're probably familiar with is conduction. So this is literally the transfer of heat via molecular contact. So the two objects are literally touching each other, and they're able to transfer heat because the molecules are jumbling around in one system, and they're touching the other system, and they kind of jumble around and transfer some of their energy to the other one. Contact. Let's finish writing. There's also convection, which is the transfer via bulk motion. And I should give some examples of all of these. So one example of conduction could be like putting your hand on a hot pan, which I would obviously not recommend you do, but it's a good example of conduction, and you can feel it really quick. So convection, an example of that, albeit a much more large-scale example, is the convection cells in the sun. In our sun specifically. So you've got these big cells of hotter matter that, due to the fact that they are hotter, rise up to the surface, and then they cool and they fall down. So you see these really interesting convection cell patterns on the surface of the sun. That's an example of convection, the transfer of heat via this bulk motion. And then also relevant to the sun is obviously radiation, which is the transfer of heat via electromagnetic waves. So we'll just say EM waves. And typically heat is going to be mostly transferred via infrared radiation. And obviously an example of that is going to be potentially something you are using during the season if you are in the Midwest and in an area that's cold right now, which would be like an infrared heater. Heater. All right. So we are now moving on to compression work. So this is section 1.5, compression work. All right, so there are a bunch of different types of ways to do the work that we showed here in the first law of thermodynamics. This just stands for work in general. For the moment, we're gonna specify that we're only gonna look at the type of work that is done via compression, namely compression of a gas. So in general, from mechanics, well, hopefully you remember that work is related to the force as a vector dotted with the displacement. Okay, so here in thermo, this is going to reference the point of contact. And I'll draw out a picture in just a second. So what we mean is we've got some system here. And let's say we've got this wall that can be moved. It seals everything off, but you've got particles of gas flying around in here at some temperature. So if we do work via compression, what that looks like is we slide this guy over to the left, for example. And the reason I said that this refers to the point of contact is because if we look at where this was originally, the delta x is referring to the distance from this point of contact here, to this point of contact. So this is our delta x, or our dr. We're being kind of loose with differentials versus finite, but doesn't really matter that much. Okay. So since in general stuff like this is actually what we're gonna be looking at is just a flat surface being pushed on some kind of cylinder, then in general, this F dot dr where we should honestly, let's just not even write differential. Let's just write delta x because it's finite. We're not integrating anything here. But in general, these two things are going to be in the same direction, right? So the force is going to be applied in that direction. So we can generally just write this as F, the magnitude, times the magnitude of delta x. So neglecting the dot product because they're always going to be in the same direction. Okay. So we might want to write this force here using the ideal gas law, for example, if we're dealing with a gas in here. So again, we know that pressure is equal to the force divided by the area, or F is equal to P times A, right? So at this point, we need to specify something about the nature of the compression that's being applied. And what we're going to have to assume here is that the compression is acting very, very slowly. Because remember, the ideal gas law, it only applies at equilibrium. Everything we're talking about in this class is just about equilibrium, okay? So what we're going to assume for the moment is that the compression acts so slowly that we can approximate every single point of the compression movement as being at equilibrium, because we're moving so slowly that the gas has enough time to respond and to come to equilibrium. So assume compression is very slow and gas is at equilibrium at all times. So what we're going to refer to this as, this is called quasi-static compression. All right, and this is obviously an idealization of reality. But it'll give us some good approximations. All right. So we have that the work done on the gas is going to be equal to PA times delta X. Oh, just got a message. So the reason that we're writing P times A here, I mean, originally we had work is equal to, where is it? Well, yeah, work is equal to F dot delta X, and then we said that we're always going to be able to write F times delta X as a magnitude like this. And then we showed that F is just going to be the pressure times the area, so all I'm doing down here is just saying that statement all at once. So the work is going to be equal to the pressure times the area times delta X. So this is the force, this is the distance being displaced. And so here, this is going to be a volume, right? We've got an area times the length. And in this case, since we're actually compressing the system, this is going to be minus delta V, okay? Because it's being compressed. Because compression. And remember that this is the work done on the gas, not the work the gas does on other things. Okay, so let's work with a really simple example right here. So suppose, oh God, it's so hard to draw straight lines. So let's suppose you've got a water bottle. And let's say it is a 1 liter water bottle. And it looks something like this. So here's the cap. Here's the little threads. And then here's the actual container that it screws into. And these numbers probably don't make any sense, but who cares? Let's just say that going from not having the cap on to having the cap on and tightening the cap, that it changes the volume. Oh, I can't even read that. Causes a compression, right? Because what you're doing is you're taking this, you're shoving that in, and that's gonna, in an ideal case where this is actually sealed off while you're doing the whole thing, that's the idealization aspect here. The part of actually screwing this in should move that further into the vessel, and it'll compress the gas inside by a small amount. So we're going to say that tightening the cap causes a compression, which changes the volume by 1/2 liter, which is absolutely ridiculous, right? So delta V is going to be roughly 0.5 liter. So in that case, what is the work? What is the work done? Now, let's say that since this cap is pretty small, it only causes a compression of, let's say, something like 0.005 liters. Okay, in this case, if I also told you that P was at atmosphere, 1 atmosphere, you could just take the formula we have written above for quasi-static compression, and you could plug everything in. You've got P, you've got delta V, and you could calculate the work, get some number over here. All right, now, what if the situation is a little bit different? What if we have this really ridiculous looking water bottle that looks something like this? It's got the cap, but then the threads, they just extend forever into the container. They go practically all the way to the bottom, and somehow they're screwing in, but whatever. Hope you get the idea of what I'm going for here. So basically, you've got a water bottle, which when you tighten it in, it's able to actually change this volume by a ton, right? So delta V here is going to be like on the order of a liter, right? 1 liter, because it's basically taking up all of the space in this bottle. So do you see anything wrong with potentially applying the formula that we had before, which is that work is equal to minus P times delta V? Is there anything wrong with that? Well, there certainly is. So in the case before, I told you that P was at 1 atmosphere, and the implicit assumption here was that as you screwed this in, as the volume changed, that the volume change was so small that it didn't actually cause this pressure to change at all. The pressure was just constant the whole time, approximately. But when you start getting into weird scenarios like this, or not even necessarily weird, but ones where the pressure will actually change as you're changing the volume by a ton, then this expression is not going to work, right? Because this P is definitely not a constant. Like dp, the more mathematical way to write this would be that dp dv is not going to be 0 or anywhere near 0. Okay, and maybe the best way to show this problem is by looking at a PV diagram. So basically just a graph of pressure versus volume. So on the y-axis, it's customary to write P, pressure, and on the x-axis, it's customary to write V, the volume. So we can kind of put our two scenarios on this graph. So for the first scenario, let's say we are going from V1 to V2. So that was the change in volume for the previous normal looking water bottle. And then going from V1 to V3, well, actually, yeah, so V is increasing. So it should actually not be quite like this. My bad. So this should be V1. This will be V2. And then this way down here will be V3. Doesn't really matter. The logic still holds. So if our graph looks something like this, with P as a function of V, and in the first scenario, we're looking at a change from V1 to V2, we're basically just looking at this little section right here. Which if we're only looking at that by itself, maybe we could convince ourselves that it's approximately linear, or it's approximately constant, I mean. But if we're moving over a large enough region of this volume space, you can clearly see that it's changing significantly. Hopefully you get the idea here. So like going from here to here, that was the first bottle. And then going from here to there is the second bottle. All right. Now, let's draw another diagram. So we know that we can use W equals minus P delta V for P equal to a constant, right? So let's just draw out another PV diagram for the fun of it. P. And let's suppose that P is constant. We're changing V. So our PV diagram looks something like this. You're going from here to here. Now, the area under this line right here, that's equal to whatever this P is. We'll call it P1. And we'll call this V2, and this V1. So the area is going to be P1 times V2 minus V1. Right? But we also had that the work done is P minus P times delta V. So basically, we can relate the work to the area. We have that the work done is equal to minus, in words, the area under the line, which is equal to minus P1 delta V for this scenario. So by considering the case where P is constant, you can see that the work is just related to the area under this line right here. So now if it's not constant, what do we do? Well, since you've all taken, I assume, at least one semester or so of calculus, you should be able to answer this pretty easily. So if we have something that looks like this, or we'll just say it's linear for the moment, call this V1, call this point out here in no man's land V3. Well, if we apply this phrase again, the work done is just going to be the area under the line, right? But how do you actually calculate the area under the line? Well, use calculus. So the area, we know, we can get just by integrating. So we'd integrate P dV. So at every single P, you integrate up the little tiny V slices and you add them all up. All right, so then in general, what we can say is that for the case of quasi-static compression, we can write the work generally as so. So we'll integrate from vi to vf. Some function p of v, it could be constant, it could be a constant function of v, we don't know, but this is the general formula. dv, and this is for quasi-static compression. All right, so yeah, I mean, in general, you would need to be given what P of V is in order to actually calculate this. But that will always be something you're able to find, or you're able to manipulate this in some way to get what you want to know. All right, so I think that'll be a fine stopping point for us right now. I think given how much we've gotten through in this little session, we should be able to finish up chapter 1 on Friday. And if I end up needing just a little bit extra after the Friday lecture, I'll just post like a 20-minute video afterward or something like that. All right, so yeah, if you've made it this far, you've watched all you need to, so now you can go relax and pat yourself on the back. All right, thanks for paying attention.